So, before we progress to showing that IP algorithms are actually polynomial time, it is good that we take a short look at what we had done yesterday. So, we will just go over it very fast. So, this is what we did in the last class, was to talk about the general framework of an interior point algorithms, where you have a starting point and then you initialize the duality measure and you solve not exactly the relaxed KKT condition, but some little modification of it using the centering parameter sigma, and that would once done, this is the way you update from a current solution to a new iterate. And then we did certain estimates which allowed us to show that when I change from estimate xk to xk plus 1, my duality measure is actually going down, because the whole aim of the interior point methods is to pull down the duality measure and force it to 0. So, our aim now is to see if our algorithm is in polynomial time. Now, it would take quite a while and it is quite technical to go into the details of what it means by polynomial time. Again, I would like to stress, looking at the wide range of audience with wide range of capabilities and backgrounds, I would say that I would like to again assert that polynomial time means an algorithm which works fine. An algorithm working in polynomial time means an algorithm is working fine, in the sense that I can tell you that the number of steps required to stop the algorithm is bounded by a polynomial, which is based on the number of data inputs, or the say x n in the Rn, the n plays quite an important role in the polynomial. So, it is a polynomial in n. So, you know that if I know what is n, I can say that within this number of steps my algorithm is actually going to finish up. There are a lot of issues here, but we are not getting into this too much of detail. So, let me start with this complexity result. The statement goes as follows, and this is from this book Primal Dual Algorithms for Interior Point Methods by Stephen J. Wright. It would be good that if you have a look at the book I am showing, I think this is a much better technique than writing it down. You could see the whole title, the publisher Siam and the author. So, let us take epsilon between 0 and 1. This epsilon, as I told you before, this is, if you look at the framework, what we intend to achieve. We intend to achieve, as we work on, till epsilon is less than equal to epsilon, till tau is strictly bigger than epsilon, we continue doing this, repeating the process. When tau is less than equal to epsilon, we stop the algorithm. So, is the accuracy parameter. So, we are driving tau to 0, we need not reach 0, but if we come very near 0, that would almost acceptable for us. So, as I want to assert you every time that optimization is not really the science of finding the exact solution, but it is really some sort of science, art and mathematics of finding something which is satisfactory, and how much satisfactory, that is a question that brings into brings in front of us a whole gamut of questions that needs to be discussed. But for us, by meaning a good or a happy thing, or something which I would be satisfied with, is that if tau is less than epsilon, that is what I want, nothing more. So, that is my requirement. So, this is my parameter. So, suppose we have the following rule, that is, you are generating a sequence where you have the following rule, that the duality parameter at the k plus 1th iteration is satisfying this expression, this recurrence relation for some delta and omega positive. Now, also assume that when you start the algorithm tau naught, the starting duality measure. So, you have the starting points x naught, y naught, s naught. So, x naught inner product s naught divided by n. So, starting duality measure is this, satisfies this property for some, maybe it is better to give a different notation for some, I guess I would say some alpha, for some alpha greater than 0. So, we are assuming this. We can devise algorithms which will actually follow this sort of property, and that is what we are going to show next, that we can devise an algorithm where this properties are followed. So, mu naught is less than equal to 1 by alpha for some alpha strictly bigger than 0. Then we are telling, then not mu naught, I am making a mistake, it is tau naught. Then there exists an index k, k is one natural number. So, x of k, that is where you stop. There exists an index k with k equal to big O of n omega natural log of epsilon. So, you see such that tau of k is less than equal to epsilon for all k which is bigger than this k. Now, this capital O of a function say f n means this is nothing but a constant times f of n, it is less than a constant times f of n. This is the meaning of big O. So, these are actually asymptotics, which tells you how fast this is moving with respect to this, how fast this quantity is moving with respect to f n. So, here it means this is nothing but some constant times this into this, that is what it means. And you see n to the power omega. So, omega is some positive number and n is obviously natural number. So, this is actually a polynomial in n. So, if I know n and if I fix my accuracy constant, I can put this and I can tell you that within these steps say some. So, I can say that k is actually like this, some constant which is okay let us for the time being, of course, we do not know the constant. So, k is not more than this. So, within this number of steps at the max you will reach this conclusion. So, that is what it tries to say. Now, we are going to try to prove what is in here. How do we prove this thing? Now, we will start with our initial expression that tau k plus 1 is less than 1 minus delta n omega tau k. Now, you take logarithms on both sides. Ln means natural logarithm log to base e. So, you can take the log because log is an increasing function. Look at those who have forgotten about this poor function called log. This is the graph of y equal to log of x, log e x, which is same as ln x. So, here if I take the log, so log is the increasing function. So, x less than y means f x less than f y. Log of x y is log x plus log y, standard result. This is what you have. Now, if you repeatedly apply this formula, now on log tau k is again less than 1 minus delta n omega tau k minus 1, and so you repeatedly apply. So, if you do that, you will get a general formula of this form, that log tau of k is less than equal to k times log 1 minus delta n omega plus log tau 0. Now, what was tau 0? Tau 0 is less than 1 by e to the power alpha. So, you can take log here also, right. So, let us see what would happen here. So, I will just do this calculation on the side in case, but this is a simple calculation, but still I will just do this calculation. So, tau naught is less than equal to 1 by, so ln tau naught is less than equal to alpha times log 1 by e. I can write also log of minus e, but this is nothing but 1 by e to the power alpha. So, the alpha comes in here, and so standard log formula. So, this is becoming kappa, okay, I will just maintain the same symbol, symbols can be misleading. So, these are all to the base e, log base e, please remember that. Nowhere in our discussion we are using log to base 10. Those who are thinking that is log to base 10, please note this is log to base e. In mathematical analysis, it is only log to base e. So, log 1 minus e, log, this is what you have. Now, once you have finished that calculation, we will use a standard result, log of 1 plus x is less than equal to x if x is greater than equal to minus 1. This is a very standard result once you know how to write the logarithm series. Logarithm has an infinite series. So, you can take up this as a homework and try it out, and you can find it in any standard analysis books. So, here I can take 1 plus x, x could be this one minus delta by n omega. So, what would happen is the following, log of tau k is less than equal to k times x is here minus delta by n omega. Obviously, this is bigger than minus 1. You can choose it in such a way that this is bigger than minus 1 delta by n omega. So, you choose your delta and n omega in such a way that this can be made bigger than minus 1. These are positive quantities, but if I put a negative one, I can choose in the sense that I can choose delta and omega in such a way that delta by n omega has to be strictly less than 1, otherwise this has no meaning, 1 minus delta n omega has no meaning. So, one has to observe that this expression is meaningful if I have this to be positive. So, 1 minus delta omega is strictly bigger than 1 minus is strictly bigger than 0. So, 1 is strictly bigger than delta by n to the power omega. So, minus delta is strictly bigger than minus 1, and so I can apply this on this part with x is equal to minus delta by omega, and I will get this result. Now, I want tau k, what I actually want? I have to find the k for which tau k is less than equal to epsilon. So, if tau k is less than equal to epsilon, then log of tau k is less than equal to log of epsilon. So, we would like to see if this is less than equal to this part, if this expression. So, if k minus delta n omega plus alpha ln 1 minus epsilon, if this expression is less than equal to log of epsilon, then it is guaranteed that log tau k is less than epsilon and tau k is also less than epsilon. So, this will at least give me what is the number of steps required to reach this. So, if this happens, this would imply this and that this would imply tau k to be less than epsilon. So, what I would now have is k times minus delta n omega plus alpha times log 1 by epsilon is less than log epsilon. Now, I will take k on the other side. So, I have to find this k. So, k times minus delta n omega minus alpha log of epsilon is less than log of epsilon. So, you see what it tells me, that for any k, for the k for which this is less than equal to log epsilon. So, if you take any k which is bigger than that k for which this inequality holds, then of course, for all such k's this will be satisfied. So, this is the minimum value of k for which this will hold, basically this expression, that is what I want to find out. So, what does it say, that if this would happen, then I would take it to this side. So, I will have k times it is much better. I think this is not the way, it is much more simpler to do it in this way. So, I will put log minus log epsilon plus alpha log 1 by epsilon is less than equal to k times minus delta by small k I am writing minus delta by n omega. Which implies that I can make log minus log epsilon is log of 1 by epsilon. So, 1 plus alpha times log of 1 by epsilon is k times delta by n omega. So, it implies that k is greater than equal to 1 plus alpha times n omega by delta into log of 1 by epsilon, right. So, what you can write simply, you see this is not, this just tells you it is in polynomial time. You can also write minus and write log mod e, that does not a very big problem. Here if you do not write in this way, here in this case instead of this you can just also write log of 1 by epsilon, does not matter, it is the same thing. Now, what is this? What does it tell you? It tells you that for any k which is bigger than this, this expression would be less than log epsilon. So, for thus tau k would be less than epsilon. So, for any k bigger than equal to 1 plus alpha delta by n omega log 1 minus epsilon, we have tau k less than epsilon, because what we have shown that if this is less than this, then k must be bigger than this. So, when k is bigger than this, we can just work out in the reverse fashion and show that this is happening. So, once this happens, then log of tau k is less than log of epsilon. So, tau k is less than epsilon. So, if I say k is equal to 1 plus alpha times delta n omega log 1 minus epsilon, this is nothing but, if I take this as the constant c, and this is nothing but order of n omega log epsilon. So, here I have expressed the whole thing as a function of the problem data. So, and that shows that the problem is polynomial time. Now, can we devise a algorithm? Can we devise an algorithm which will actually follow all this property and follow this sort of polynomial time framework? Can I devise something? So, that would lead us to the study of path following methods. Obviously, all the methods are path following except the potential reduction ones. Path following methods. So, we are first talking about the short step method. So, what does this short step method do? In the short step path following method, we have to realize one thing. We know that if I project, say, my central path onto the excess space, in this case just we are looking at two variables because that is the way we can visualize it, and the projection here is nothing but the central path's projection is nothing but straight line through the origin, because x1 s1 equal to x2 s2. So, this is a straight line which is dividing the orthant into two equal halves. Now, once I solve the equation which is here, once I solve this equation, I am not exactly getting the solution of a point which will take me to the central path, or I am not exactly solving the relaxed KKT condition. So, as a result of which what I would get is not a point on the central path, but some point near it. But we cannot allow these points to wander off too much, that is, we cannot allow these points to come near the boundary where one of them x1 or s1 can drop to 0, x1 s1 or x2 s2 can drop to 0. So, that is what we cannot allow. You cannot allow the points to come away too far from the interior and more towards the boundary. That is what the barrier does, it stops you from going to the boundary. Now, we have to then somehow force these points, these solution points, these approximate solutions actually, to stay in a region near the central path. So, we have to define what is called the neighborhoods of the central path. Okay. So, there are two types of neighborhoods, and one is called shorter neighborhood, a neighborhood which allows short steps, that is the short step method. Another one which allows you more flexibility, and that would be used for the long step. So, what we will use now is the following neighborhood. So, we will write down the two neighborhoods. Now, this is an element of f naught, and I want to again remind you that f naught is nothing but f d cross f naught p cross f naught d e, which you already have seen. So, this tells you that the standard Euclidean norms finding the distances, standard distance finding thing, distance finding computation. So, once you know the duality measure at a particular point, find all such points which are of this form, that corresponding to this tau is the duality measure, that is x inner product x by n. This has to be bounded by theta times tau, where e is obviously 1 1 1 1, the vector of ones. So, theta is a quantity which could be 0, but cannot become 1. So, I am defining a neighborhood. So, another neighborhood which we will also use, which is called the infinity neighborhood or large neighborhood. What they are trying to do? They are trying to see this much, how much you are far from your duality measure, how much you are far from the duality measure, and that is exactly what they are trying to see, how much you are far from the duality measure, to what extent you are violating this thing, this duality measure. So, let me write down the second one. So, you take a gamma which is between 0 and 1 will now really be concentrated on this neighborhood rather than the one I am just writing, but this is just for your information at this moment. So, when we do it we will not mentioning again. So, for us it is important to know how this sort of neighborhoods look like. If you look at this, how this sort of neighborhood looks like. So, what is this? This is a Euclidean norm, right. Okay, this square is less than theta square tau square. Now, what is the meaning of this? So, what is excess E? Let us look at again just to remind you, this is nothing but this vector. And E is 1 1 1 and tau is nothing but tau 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 tau, tau E is nothing but all components are tau. So, basically if I look at it, this would give me nothing but x1 s1 minus tau whole square plus xn sn minus tau whole square, which is less than equal to theta square tau square. Now, each of them has to be less than this quantity, because these are all non-negative quantities, a positive quantity is adding up to a quantity which is less than a positive quantity. So, each of them must be less. So, what I am having is say tau I si minus, so xi si minus tau is less than theta square by theta square into tau square. So, this would just give me that, which simply means we can just directly write down from this. This is what it means, which means that tau minus theta tau is less than xi si is less than tau plus theta tau, which means xi into si for every I is 1 plus theta into tau 1 minus theta into tau. So, if for each I x, so here x1 s1 x2 s2 is both within these two limits, right. So, it changes. So, what does it says that x1 s1, so x1 s1, this is say x1 s1 and this is x2 s2. So, s1 s1 is within certain limit, x2 s2 is within certain limit. So, I want all points within this. So, at a particular choice of xs. So, if you take the Cartesian product of these two, this is what sort of a, for a, so any point x y s which is here has to satisfy something here. So, any point of this form x1 s1 which is say I have given the theta and this is my tau, tau also keeps on changing. So, what you are having is at every point you take around that you are basically creating these sort of small squares. Of these sort of lengths, the squares, the maximum length that you can have. So, it is between 1 minus theta into tau into 1 plus theta into tau. So, within that limit everything should lie. You can keep on changing the x and s's, the taus will keep on changing. So, the lengths of the squares would change. So, basically you would have something like this. So, if you really draw this up a bit, so this will be some, if you as your theta or tau becomes 0, the size of the squares will keep on decreasing. So, basically if you look at, you take the edges of the square and try to draw some sort of a tube. So, it will be something like this. Now, this is your n2 theta. So, what is happening with this n2 theta is that you can now start from a point here, move to a point here, but the algorithm should be such that that is what I will show you. The short step method would be such that you are always remaining within this n2 theta. But you cannot make very large steps, cannot take large steps, because you will then there is a chance of you getting outside n2 theta. So, because you cannot do that, this is called a short step path following method when you use such neighborhoods. This neighborhood would allow you to be much more flexible. So, let us just for the time being write down the short step path following algorithm. Short step path following algorithm. So, initialization step. You will create the neighborhood n2 theta, so that you force all the points there, that is this sigma, the centering parameter is 1. You will see these choices are helpful, because with these choices you can show that the whole algorithm is in polynomial time, and your starting point you have to guarantee not lambda s y not, the starting point has to be in, this guarantee has to be taken. So, of course, you may say that, oh, I cannot really find out such a thing, I can just find out a point which might be infeasible. Then there is something called infeasible interior point methods, where you start with an initial infeasible point, but after certain successive steps you get a feasible point. So, but just for this simple explanation of this toy algorithm, we are essentially taking this fact that we are already in the feasible set. So, now, so do I loop? So, for you said, so sigma is k is not adaptive, it is not changing, it is fixed, and solve the equation, solve the equation star. So, this is what you have to do, you have to solve the equation star. Obtain delta x k, delta y k, delta s k, and write. So, you are doing a for loop for k equal to this, do this, do this. So, it is the next. Now, here what you take is a pure Newton step, you do not have here a scale which is less than 1, a scaling parameter or a control parameter which controls how much you move from the iterate x k, y k, s k in the given direction. So, along the Newton direction, this is the Newton direction, obtain this is, or the relaxed Newton direction, maybe I should write relaxed Newton direction. So, you add this to, so this is how you keep on doing, and then you have to, this is your basic algorithm, and you end the for loop. So, this is, you keep on doing this till you have tau less than epsilon, epsilon has to be put in as per as your requirement, end for. So, this is the short step path following algorithm. Now, tau k plus 1 we have shown earlier, if you remember this estimation that we did, what did we do? This is the estimation, tau k plus 1, in this case of course is depending on alpha, here alpha is nothing but 1, here if you look at this, I have no alpha here corresponding to what was here, there was an alpha here between 0 and 1, my alpha I have chosen it to be 1 in the short step path following method. So, you have alpha equal to 1. So, tau k plus 1, if you again go back and see the calculation, the tau k plus 1 is 1 minus sigma into tau. So, in this particular case, just let me write down. So, if when I take alpha equal to 1, this 1 and 1 will cancel, and you will have sigma into tau. In this particular case, tau k plus 1 is sigma into tau k, and what is sigma? 1 minus 0.4 by root n tau k. So, here my delta is 0.4, which is same as theta. My delta in, so here I am having everything in the form this, and my delta is 0.4 and my omega is half. Omega is half. Now, what does it show? I am actually having a scenario of this result. I am actually having the basic requirement of proving the complexity or the polynomial time. Only if I choose my x naught, y naught, s naught in such a way such that tau naught is less than 1 by epsilon by alpha, then I am done. Then I have already put the sequences in this form, then I am just already I am straight done. So, I just have to choose x naught, y naught, s naught such that tau naught, which is nothing but 1 by n inner product x naught s naught, this tau naught is less than 1 by epsilon to the power alpha for some alpha greater than 0, where alpha epsilon is my chosen parameter, that depends on what you choose. So, then you immediately know that you would have a polynomial time algorithm, because the basic equation is already satisfied by your choice of delta and omega. So, we have learned quite a bit of stuff today, that the general IP method, the general format under certain mild conditions can be shown to be polynomial time. We have created an algorithm called short step path following algorithm, where all the points that you generate by solving the equation star is forced to remain in a very narrow cone, and that those points do not allow you to move very far off from the central path, but keeps you near the central path. So, that is why it is called a short step path following algorithm, and we have showed that this short step path following algorithm can be easily made to follow the polynomial time pattern. And now, okay, we have done our first step, polynomial time game is over, we have proved that it is, we can show it is in polynomial time. But what important stuff that we have to show is that when I compute x k plus 1, y k plus 1 and s k plus 1 from x k, y k, s k, then I must be sure that this x k plus 1, y k plus 1 and s k plus 1 is also in n2 theta, and that is what we will discuss tomorrow, that how can we show that this is in n2 theta. Tomorrow's discussion will concentrate on that, and then we will show some more little bit more algorithms before we wind up this discussion on interior point methods. Thank you very much.